Okay, we're also going to do a few proofs in section 5.2 on proof by contradiction. We're going to do the first three proofs that don't involve rational numbers. We'll save the rational number proofs for next week. Notice it says start with the three prisoners problem. That involves having several people do a demonstration, so we'll wait and do that next week as well when I see you again. Okay, so what's the point of a proof by contradiction? So suppose you're trying to prove some statement P, and maybe you just don't have enough to work with, or sometimes you're trying to show something that's a negative, right? Like our first proof, for example, says show that there is no smallest positive real number, right? It's trying to show that something exists. Sometimes it isn't so hard. You just find it, right? But here you have to show that something doesn't exist. It's a negative result. So sometimes that's a clue that proof by contradiction will work. Now, what's the theory behind a proof by contradiction? So let's suppose we're trying to show P is true, right? That's in a proof. There's a statement P like this one. You're trying to show the statement is true. Well, instead of proving this, say directly or contrapositive like we talked about, let's look at not P, okay? If you can show not P is false, right? If you show not P is false, that means P is true, okay? Right? So the negation of this is this, so the negation of this will be this, okay? So that's the idea behind proof by contradiction. You assume the negation of the original statement, assume the negation, show that that has to be false, okay? So if the negation of P is false, that means the original statement is true, okay? So it's just another method of proof. Okay, so again, notice we're trying to show there is no smallest positive real number, okay? So let's we prove by contradiction, okay? So again, what's the method of contradiction? Assume the negation of this statement and show that that can't happen, okay? So we're going to prove the negation is false. Okay, so this is why we did all this stuff at the beginning of the course with the logic on how do you negate statements, because we need this for proof by contradiction. So we're going to assume the negation here. So there is no smallest positive real number. The negation would be assume there is a smallest positive real number, and let's call it something X. Okay. See, now we actually have our hands on something. We assume there is a smallest positive real number, and we're calling it X. Okay, so X is the smallest positive real number. Right? So we have to show that this is false. We have to run into a problem. So if there were a smallest positive real number, we have to run into a problem. That means that statement would be false, which means the original statement is true. Now you know we can't have a smallest positive real number, but let's convince the reader, okay, why does that have to be true? We have to be precise. Well, if we could create another positive real number that's smaller than this one, that would be a problem, wouldn't it? We just said this X is the smallest positive real number. If we could find another positive real number that's smaller than that X, we have a problem because we said this was the smallest. Well, how could we create a smaller positive real number? Well, the logical thing might be you have X, let's subtract something from it. Let's look at X minus 1, for example. X minus 1 would be smaller than X, but what's the problem? You don't know that X minus 1 is positive, okay? So we need, and X minus 1 would be a real number because X is a real number. So we need a real number that's positive but smaller than X. Okay, well, there's several ways you could do this. I'm going to take 1/2 X. Now again, the word consider, and when you write a mathematical proof, often you're saying you're just pulling this out of thin air, okay? So if I have this number X here, I'm going to consider 1/2 X. Now, X is a real number, so 1/2 X will be 2. If you take half of a real number, you still get a real number. So since X is a real number, we have 1/2 X is also a real number, right? Also, since X is positive, we conclude 1/2 x is positive, right? If you take half of a positive number, you will still have a positive number. Now, do you see what I'm doing here? I'm trying to convince the reader 1/2 x satisfies positive and satisfies real number, okay? So this new number that I've chosen satisfies these two conditions. Now, what's the other thing we need to address? So there's no contradiction yet. We need to argue that 1/2 x is less than x, right? Finally, 1/2 x will be strictly less than x. If you take a positive number and take half of it, you're going to get smaller. Now, what does this mean? I just constructed 1/2 x, which is positive, and it's a real number, and 1/2 x is less than x. Okay, so what do we have? This contradicts, I'm stating the actual contradiction, the assumption that x is the smallest positive real number. Okay, so I assume there was a smallest positive real number, x. I created another positive real number that's smaller than x, so that contradicts the fact that x is the smallest, because I found something smaller. And just like we did with contrapositive and with cases, you really should write a conclusion. Hence, there is no smallest, I'm just restating that there no smallest positive real number. And there's the end of our proof. Now, sometimes in a proof by contradiction, I mean, this doesn't have hardly anything in the hypothesis, but sometimes you have a long list of conditions in the hypothesis when you do proof by contradiction. Sometimes you use some of those conditions and you contradict one of them. Like if you had assumed this, suppose you had 7 things you assume, you may use 6 of those assumptions and show the 7th one isn't true. Okay, that's the sort of game you play here. So here we just contradicted the fact there's no smallest by finding there is a smallest by finding a number that's smaller, a positive real number. Okay, that's the first one. Let's look at this next one, number 16. So this number 16 involves divisibility. Now notice the conclusion on here. Let A and B be integers with A greater than or equal to, then A doesn't divide B, or A doesn't divide B plus 1. So think about if we were trying to do a direct proof, right? If we were trying to do a direct proof, we would assume A and B are integers with A greater than or equal to. You'd have to show A doesn't divide B or doesn't divide. Showing something doesn't divide, you can't get your hands on it, right? If x divides y, you can write y as kx. You can make an equation out of that, divisibility. But here, if something doesn't divide, that means you can't write it as a certain equation. So that's not very useful. So let A and B be integers with A greater than or equal to 2. Then A doesn't divide B, or A doesn't divide B plus 1. You could think of this as an if-then statement. If A and B are integers with A greater than or equal to 2, then, right? You can think of this as an if-then. So if you think of that as an if-then, well, we did ones like this that involved the contrapositive, right? We don't like the negative result, like A doesn't divide B, A doesn't divide B plus 1. What if we did contrapositive? Then you would assume A divides B and A divides B plus 1. That would be the negation. What would you have to show? You'd have to show the negation of this. So what? So A and B aren't integers, or they're both integers, but A is not greater than or equal to 2, so A would be less than 2. That's kind of confusing. It's not very workable. Right? Let's talk about contradiction, which is how we're going to do this. So we prove by contradiction. See, notice when we do proof by contradiction, we're going to have more to work with. Right? Contrapositive, we would just have, A divides B and A divides B plus 1, and you'd have to show that that doesn't work. Right? How do we do a proof by contradiction? Okay, so what do we assume here? Remember, if you have P implies Q, think of this as if P then Q. To prove by contradiction, you assume the negation. What's the negation of P implies Q? Remember, that's P and not Q, right? So for contrapositive, you would just assume not Q, and you would show not P. But for contradiction, what do we assume? We get P and not Q. So we have a lot to work with here. So we're assuming the negation holds. So assume A and B are integers with A greater than or equal to 2. A divides B and A divides B plus 1. Remember, the negation of an OR statement by De Morgan's is A divides B and A divides. So you negate those and change the OR to an and. So do you see the advantage of contradiction here? We get to assume P, and we assume the negation of Q. So we have A and B are integers, A is at least 2, A divides B, and A divides B plus 1. We have a lot to work with here with contradiction. Whereas contrapositive, you would just have the negation, you would just have this, and you'd have to show that that doesn't hold. Okay, so that's a little messier. Now, what's one advantage of proof by contrapositive, right? So if you were trying to show if P then Q, with contrapositive, what do? You assume not Q, and you show not P, right? So with contrapositive, you assume this, you know what you're trying to show, right? You're trying to show not P. Now, what's one bad thing about proof by contrapositive? The good thing is we assume a lot. But what's the bad news? The bad news is you have to run into a problem and you don't know where the problem is. So that's one bad thing about contradiction. You have to run into a problem and it's not always obvious what the problem is. Okay, so let's just go with our gut here. Well, we have A divides B and A divides B plus 1. Okay, so what does that mean? If A divides B, that means B is KA for some K. I'll write that in a second. And if A divides B plus 1, that means B plus 1 is MA for some K and M in Z. Right? That's a definition of divisibility. If A divides B, B is a KA. And if A divides B plus 1 is an MA for some integers K and M. Okay, fine. So we have these two equations to work with. Again, we have to come up with a problem, with a contradiction. Right? What if I subtract these two? Okay, then, and this is the sort of thing, I'm doing this example to show you this technique and maybe you can use it in other problems. Okay, now I would have already done the scratch work. Hopefully you'll follow what I'm doing here. Okay, so I'm going to start with 1. Isn't 1 B plus 1 minus B? Again, you say, why in the world am I doing this? You will see. Okay? B plus 1 minus B is 1. B plus 1 is MA. And B is KA. Okay, so I have 1. B plus 1 minus B is 1. So this is a true statement. B plus 1 we said is MA. And B is KA. And this is just begging for me to factor out an A. Okay? So this is a true statement. Again, you may say, where are you coming up with this? You'll see. Again, I'm showing you this. This may not be something you come up on your own, but I'm showing it to you so this idea will be in your head in the future maybe. Okay? Now, again, with divisibility, I'm not making you say everything about integers. Notice nothing's being divided, right? So everything's being multiplied, added, and subtracted. So we said M and K are integers. We know M minus K is an integer, okay? So I have A times this integer is 1. Well, what's a word I haven't used? Thus. Right? If A times M minus K is 1, and M minus K is an integer and A is an integer, that means A divides 1, doesn't it? That's a definition of divisibility. Right? If A divides 1, 1 is A times some integer. That's what we have. Okay, so far so good. But now we've run into a problem, haven't we? We assumed A was at least 2. A is an integer, A is at least 2. If A is a integer greater than 1, how can that number divide 1? Right? if A is 2, 2 doesn't divide 1, 3 doesn't divide 1, 4 doesn't divide 1. Okay? So since A is greater than or equal to 2, we have a contradiction. So notice it's not obvious at all what the contradiction was going to be. But if you play this little game and subtract these two, I get 1 is a multiple of A. A divides 1, but A is at least 2, which means that number cannot divide 1. Okay, so we assume the negation was true. We negated this statement, right? P and not Q. We ran into a problem. The negation is false. Therefore, the original statement is true. So therefore, if A, B, and Z with A greater than or equal to 2, then A doesn't divide B, or A doesn't divide B plus 1. And there's our proof. Okay? So again, let me summarize what we have so far. With contrapositive, what's the nice thing about contrapositive? When you negate the Q and assume that, you show not P, so you know what you're trying to show. Okay? So at least you know what you're getting to. But sometimes assuming the negation of Q is not enough to work with. What did we do here? We did a proof by contradiction. You negated the if-then statement. So it was P and not Q. So we had all this information to work with. But what's the disadvantage? You don't know what you're trying to get to. You have to run into a problem somehow. Okay? I mean, I could have written this another way. I could have said, remember I mentioned earlier that sometimes you contradict a condition you've written. I could have said A divides 1. Well, if A is an integer and A divides 1, what does that mean? A is plus or minus 1. Right? If an integer divides 1, A would have to be plus or minus 1, which contradicts the fact that A is at least 2. Same argument. Okay, I could have figured out what A is. A would have to be plus or minus 1. It said A is at least 2, so there's your contradiction. Okay, so let's do one more here. This is number 15. It's another divisibility proof. Okay, so it says if A and B are odd integers, if A and B are odd integers, then 4 doesn't divide A squared plus B squared. 4 doesn't divide A squared plus B. Okay, so again, let's argue our different methods of proof. Direct proof, assume A and B are odd, no problem. Show 4 doesn't divide something. It's a negative, right? 4 doesn't divide means you can't write A squared plus B squared as 4 times an integer. So that's not very user-friendly. What about contrapositive? Assume 4 divides A squared plus B squared, the negation. Show the negation of this, so either A is even or B is even. That doesn't sound too bad. Okay. Now what about contradiction? Again, I'm going to do it with contradiction, just as another example. Keep in mind, sometimes you can prove a result with a direct proof. Sometimes you could also maybe do it with contrapositive and also do it by contradiction. So sometimes it's just a matter of choice. So we prove by contradiction. I don't really like proof by contradiction, only because what I said before, sometimes it's hard to figure out what fact to contradict. But sometimes that's all you've got. We prove by contradiction. So this is an if-then statement. What's the negation of if P then Q? It's P and not Q. So we assume A and B are odd integers, and 4 does divide A squared plus B squared. So we have stuff to work with here. A and B are both odd. That says and. A and B are both odd, and 4 does divide A squared plus B squared. So we have a lot to work with here. Maybe we should... there's several ways we can do this. Let me focus on the odd. Thus, A is a 2k plus 1, and b is a 2m plus 1, say, for some k and m and z, right? That's a definition of odd. Okay. Let me just keep going with this. We're interested in something divided in a squared plus b squared. I'm just going with my gut. Let's look at a squared plus b squared. So, a squared plus b squared is 2k plus 1 squared plus 2m plus 1 squared. I'm just going with my gut. This was a game we played with other proofs we've done with odd and even, right? Once you get a as something and b as something, we just substituted. Now, if we work this out, you get 4k squared plus 4k plus 1 plus 4m squared plus 4m plus 1. Okay. Equals. Okay, I'm going to do something in one step. Again, if you think your reader is not going to be able to do this in 2 steps, write it out. But just to save a little bit of time here, I'm going to factor a 4 out of all the terms that have a 4. So k squared plus k plus m squared plus m, and then I have a plus 2 from the 1 plus the 1. Okay. So I've sort of milked what I can from the a squared plus b squared, but using a and b are odd. I haven't done anything with the 4 divides a squared plus b squared. So let's look at that for a second. Okay, so now I'm shifting gears. So since I haven't used this, I'm reminding the reader of this fact. Since 4 divides a squared plus b squared, we have a squared plus b squared is 4, I use the k and an m, h, 4h for some h and z. Okay. So I focus on the odd and the even. Again, why did I plug into a squared plus b squared? Because I had that expression here. Now again, we're doing a proof by contradiction. We have to run into a problem somewhere. Notice I have a squared plus b squared is 4h. Here I have a squared plus b squared is 4 times that. So both of these are a squared plus b squared. So it follows that. I'm just going to piece this all together for the reader. So I have, from here I have 4h is a squared plus b squared. But from here I have a squared plus b squared is 4 times k squared plus k plus m squared plus m plus 2. Notice I wrote this one first just because I did it right here. And then this one's coming from here. Now, why did I put the 4h plus? Because again, when you write a string of equalities, a lot of times you're interested in what's on the ends. I have 4h is this. Okay. So I just used the a squared plus b squared to get these two were equal to each other. And again, you may want to tell the reader what you're doing. I'm interested in these two. So subtracting 4 times k squared plus k plus m squared plus m from both sides of the preceding equation, or the one right above, yields. So what do we get? I'm subtracting this long expression from both sides. I get 4h minus 4 times k squared plus k plus m squared plus m is 2. Right? So I'm not concerned about a squared minus b squared anymore. I just use that to get these are equal. So 4h minus that is equal to 2. Okay, let me come back up here. We're almost done. Okay. Thus, notice I have a 4 in both of these expressions here. Let me factor a 4 out of that. I get a 4 times h minus k squared minus k minus m squared minus m is 2. Right, factor a 4 out of both of these terms and distribute the minus sign. I get h minus k squared minus k minus m squared minus m. Okay. And again, you don't have to state this. With divisibility, we know everything's an integer. H and K and M are all integers. The squares are integers. You subtract, you get integers. So notice what we have here. It's the same flavor as the one we just did. 4 times an integer is 2. So what do we conclude here? We conclude that 4 divides 2. 4 times an integer is 2. That means 4 divides 2. But 4 doesn't divide 2, and there's a comma, a contradiction. So again, we didn't contradict any sort of assumption we made. We just ran into a problem with divisibility. Notice, right, there's no variables here, right? I don't need to explain that. 4 divides 2 doesn't make any sense. That means 2 is 4 times an integer, right? This means 2 is 4 times an integer, which isn't true. So notice we reached a contradiction, and so we're done. We assume the negation of the statement was true. We assume the negation was true. We ran into a problem, so the negation's actually false, which means the original statement is true. So therefore, if A and B are odd integers, then 4 doesn't divide A squared plus B squared. So notice the game on this one and the one we did before was, use the fact about divisibilities to get that something divides something, which isn't true. Okay, so that got us through the proof with divisibilities, and the first one with no smallest positive real number. So next we'll define rational number and irrational number and do some proofs involving those.